Hey everyone, welcome to the blood gas transport lecture of our respiratory system chapter. I'm going to start off with a very brief review of something we've already covered. It was to do with our blood. So this is a hemoglobin molecule and it's found in our red blood cells. But each of these have this unique kind of feature that as oxygen binds to each one of these globin molecules, or in particular with the heme group here, it'll cause a shift or change in shape of the hemoglobin molecule, okay? And that's going to be really important as far as what our discussion is moving forward, because what we're going to talk about is how well oxygen can bind to hemoglobin. In particular, when we have this conformational change in shape, we have one oxygen bind, it shifts the shape and actually increases something called the affinity, or the capacity, or the likelihood that another oxygen molecule is going to be attracted to and bond to another heme, which then causes another change, which further increases the affinity for a third oxygen, similarly increasing the affinity for a fourth oxygen to bind to hemoglobin. So we see this increase or cooperation of increasing what's called the affinity or the likability of oxygen to the heme group in hemoglobin. Okay, so that was some new information, some review, but just to kind of set the context here of a really important concept as far as how oxygen and we'll later discuss carbon dioxide gets transported in your blood. Okay. Shockingly, there's only about 9 to 15 milliliters of oxygen that is carried or dissolved in our plasma, and that in and of itself is not sufficient to meet all the energy demands of our body. So what does our body do? We've managed to develop this great thing, a red blood cell, that is able to again pull in, attract, and hold on to oxygen within it and disperse it as we get to different parts of the body that need it. There's a really, and that's what we'll be looking at today and how that happens. One thought, though, to remember, just as far as the structure and the anatomy of a red blood cell, is that it doesn't have a nucleus and it doesn't have mitochondria in it either. So that kind of explains its shape. Originally, red blood cells, when they're forming, would be spherical, but again, they lose the nucleus and then they lose the mitochondria, so they don't have as many organelles in them, and therefore they get this kind of concave disc shape that we all know red blood cells, or have seen red blood cells to have if you've seen any of my microscopic views or images of it. Okay. And the importance behind that is, if a cell doesn't have any mitochondria, it means there's no oxidative respiration occurring. And that's important because if we're carrying and trying to deliver oxygen, we don't want red blood cells utilizing that oxygen for energy production. So red blood cells only use glycolysis to produce energy, and so therefore they're anaerobic, which means no use of oxygen, which means all the oxygen they carry, they're going to keep. You don't want to use the product that you're delivering, right? So, okay. Great, we spoke about this, but the two terms that I'm not sure I specifically used yet was oxyhemoglobin, so that's hemoglobin that when oxygen is bound, and deoxyhemoglobin is when hemoglobin does not have oxygen bound to it. And as mentioned before previously, when we increase the amount of globin groups that have oxygens bound to it, or increase oxyhemoglobin as far as the contents of red blood cells, we have more and more oxygen. Okay. And so what we end up getting with that increasing affinity is something that looks like this. And this actually explains more or less pretty much all components of our blood delivery system, or our oxygen delivery system by blood. So let's just take a look at what's going on here. Again, always looking at our excuse me, X and Y axis first. So here along the bottom we see our partial pressure of oxygen, so our PO2 in millimeters per mercury. And then we have a percent of oxyhemoglobin saturation here, going from 0 to 100%. And hopefully some of these numbers down here make sense to you a little bit. Again, recalling that in the lungs, in systemic arteries, in blood, we're at about 100 millimeters of mercury as far as our partial pressure for oxygen. And again, if you recall, in the veins, it's about 40 millimeters of mercury. Those are good numbers to know and have memorized. So how do we read this chart? Well, we see that there's a sigmoidal curve. We have something here about the 40 partial pressure of oxygen gives us about 75% of a fully loaded hemoglobin, right? So oxyhemoglobin means oxygens are bound to hemoglobin. So as far as the total percentage of our oxyhemoglobin, we're at about 75% when we're in the veins, okay? So again, blood in veins. When we get back to the lungs, or you can look at the arteries, arterial blood, once oxygen is fully loaded up, we get to 100% saturation, and that's a great thing. And when we're at rest, this is how things work, right? We essentially move between 100 and about 25% less saturation in our oxygen. And actually most of the time, if you're to take a measure, you'd read it quite high. It might be 98% saturated when we're just at rest. If you ever see the pulse oximeters, the little finger clips that you might see patients, or you might have had yourself at the hospital wearing, that will measure this, is your oxygen saturation. So again, it remains quite high systemically at our fingertips, etc. When it gets quite low, would be just in the venous part and tissues. Okay. There's a lot of writing here. Try not to read it all quite yet. We'll go through a few points and then relate it back to the curve. Okay. So in places, and just to set a little bit more context here to our discussion as we go through this, it's good to try to imagine where and how this curve shifts and what influences it in regards to where you might be in the body, whether you're closer to the lungs or closer to the tissues. And that should help kind of shape your view as we go through some of these points here. Okay, so the first thing that we'll look at is partial pressures, okay, in particular of oxygen. So when we're in the lungs, we have high partial pressure of oxygen. That should make sense, right? Okay, at that point in time, we have, as I mentioned, almost 100% saturation. So all four oxygens are loaded up onto a hemoglobin molecule, or all four globin subunits. Even if the partial pressure of oxygen decreases slightly in the lungs, that doesn't really change how our saturations levels work. Because if you notice, there's a bit of a plateau here. In particular, if we're looking at even 80, the partial pressure becomes 80 millimeters of mercury, we still get near 100% saturation, and that's great. Okay, and again, that speaks to the increasing affinity of blood to oxygen overall. Okay, good. When we have low partial pressure of oxygen, we come across that at the tissues, right? So our tissues, they want more oxygen delivered to them. We recall from last lecture that there's that pressure gradient of oxygen where it's higher concentrations in blood, lower in the tissue. So it gets pulled into working tissues in particular, like skeletal muscle, greater because it passes down the diffusion gradient. And at rest, as I mentioned, the PO2 is not that low, so in venous blood, as I mentioned. So only about 25% of hemoglobin is released, even at the tissues. So again, this is at rest. The difference is when we start exercising, okay? So the tissues obviously needing a lot more oxygen for anaerobic respiration, and so 90% of oxygen is released from hemoglobin. So how does that look on this curve? Where could we find that information? Well, if we look here, and we'll go here. We'll say that the partial pressure in tissues drop significantly low. So they're really, really working. They're very low as far as the available oxygen within tissues. Say about 10. We can follow where this curve is, and we can just move over. Sure enough, that's about 10%. So at that point in time in this dissociation curve, what this is saying is most of the oxygen dissociates from the hemoglobin, and that's a great thing. We want that to occur when we're at working tissues that demand oxygen. So we need most of our oxygen dissociating from oxyhemoglobin to become deoxyhemoglobin. Okay, so hopefully that makes sense. And so again, we just see this like, it says dumping here, but just releasing and letting go of a lot of our oxygen once we get to the tissues. Okay. So that was to do with partial pressures and how that kind of works with the dissociation curve. But let's consider something like temperature. So temperature has two effects that influence the affinity that hemoglobin has for oxygen and how the curve changes. Okay, so we'll take a look at this in a couple of different ways. So the first way here is an increase in temperature. So you start working out, because when we work out or exercise, or our bodies, our skeletal muscles produce heat energy as a byproduct of us exercising. And what happens is it leads to a shift to the right with our oxyhemoglobin curve. And we'll take a look at what that means in a moment, okay? But just kind of hold that in the back of your mind for now. It also decreases the affinity for hemoglobin and between hemoglobin and oxygen. So again, affinity is that attraction or likeness of two things together. So it decreases how well that affinity occurs, and it causes more oxygen to be released. So now if we just pause and consider that one point for a moment. If we're exercising and temperature starts increasing, but even just the exercise component alone, we know that we want to we want more oxygen reaching our cells for oxidative metabolism, or respiration, sorry. So this is a good thing that we have more oxygen being released from hemoglobin. Okay. And then the opposite, if you will, happens when we have a cooler temperature. So, say walking around outside without a coat, core temperature starts dropping. A shift to the left will occur. It increases the affinity of hemoglobin for oxygen, and less oxygen is released. Therefore, less oxygen is delivered to your tissues. All right. It's a little bit of a protective mechanism, but let's take a look at what these curve shifts mean ultimately as far as the affinity and how that works with the partial pressure of oxygen and percentage of saturation. What this means, so we'll start with the shift to the right. This being nominal or more homeostatic temperature, this being greater body temperature. And so we can see that this downward shift means we actually, for any given partial pressure of oxygen, let's go with 40. So with 40% a partial pressure of oxygen, we see that it has a lower percent of saturation by oxygen here relative to that same partial pressure of oxygen 40 at a more normal state, which gives us about 70 or 75% saturation. So again, I'm going to just kind of say that one more time for you. So at the same 40 millimeters of mercury, if we have a shift to the right, we have a lower amount of saturation of hemoglobin with oxygen loaded up. So it's less oxygen loaded, okay, relative to this. Okay, so why does that matter? Well, what that means is we have more oxygen unloading. Okay, so there's a lower affinity of oxygen to hemoglobin and a greater propensity for this oxyhemoglobin to unload its oxygen. Why might this be good? Again, we want more unloading of oxygen when we're exercising, so that increases the temperature. So this is a good thing. And then again, how do we read this if we're trying to figure out? We're gonna have to go way back. I'll just look at the 20%, not the 10. But if it's really cold out, our core temperatures are dropping quite a bit. We go all the way down to 20, partial pressure of 20 millimeters of mercury. We travel up, and we see that we have a higher affinity of oxygen to hemoglobin. So at that, let's do that. So at that lower partial pressure, we have a greater amount of saturation of our blood. So it's holding on to oxygen more. And if our metabolism is slower, that's an okay thing. But again, going up to 40, we can see we're almost fully loaded up there. At about 90% saturation when we're at partial pressure of 40 millimeters of mercury. And where does that happen again? Just as a reminder, that's in the veins. Okay, so this right shift is what we see with exercise, and that's what we more commonly speak about. So you might have noticed that it says temperature and acidity. We'll now look at another factor, that was temperature. So increasing temperature, shifts to the right, decreases affinity for oxygen, increases unloading. Well, let's take a look here. What might we expect if we're exercising? Well, we might expect that our blood becomes more acidic, right? So let's see. So here we have our normal arterial acidity. So this is kind of our baseline, our oxyhemoglobin dissociation curve. But what if things get more acidic? So we notice the number gets smaller. That means more acidity, right? Lemons and things that are very acidic tend to be closer to have a pH of 2. Baking soda and things that are more basic tend to be closer to, say, 12, maybe up to, So just an example of acid and bases and what numbers we'd expect to see for their pHs. But back to the curve here. So we have our normal dissociation curve here. We have a higher acidity. Again, higher acidity is associated with increasing exercise. And sure enough, we have a shift to the right here, which again decreases oxygen affinity and increases oxygen unloading. Okay, so at the same partial pressure, say of 40, so venous blood or getting closer to the tissues, we see a lower saturation of blood relative to that same 40 number, which has much higher when we're at baseline or at rest. So exercise, more unloading of oxygen, therefore lower saturation than that same partial pressure at rest, which has a higher saturation or less oxygen unloading. Okay, hopefully you're hearing the theme and and starting to get the pattern here. So again, increased acidity means exercise, shifts the curve to the right, decreases affinity for hemoglobin, for oxygen, increases oxygen delivery to tissues. Do we like oxygen delivery to tissues that are exercising? Definitely, because we get our oxidative respiration occurring, right? Okay, and then opposite happens for a decrease in acidity. Okay, next factor, and we got two more to discuss, is this molecule. We'll shorten it 2,3-DPG, which is diphosphoglycerate, or 2,3-diglypho. It's a mouthful. That's why we abbreviate it, right? 2,3-diphosphoglycerate. Again, has a very similar baseline curve, but when this molecule increases, we see again a shift to the right. So even without necessarily knowing exactly what it is or given any context for this molecule, if we're imagining a shift to the right of our dissociation curve, it's probably a good educated assumption or guess that it's likely to be involved with exercise. And sure enough, if you would have guessed that, 100% right, A+, etc. You can see, well, I guess it's maybe not obvious here, but this is a molecule involved in glycolysis. So it's an intermediate molecule that will be produced. So if you think about our bodies going through glycolysis, producing some ATP, and we're getting an increased amount of 2,3-DPG, our affinity in our red blood cells that pick this up will shift to the right and therefore decrease their affinity for oxygen. And again, just like all the other factors so far, I know I sound like a broken record, but there's a good point to this, is that when you decrease affinity for oxygen, you increase the unloading of oxygen to tissues. When we are exercising, we have all these feedback indicators. So far we've spoken about temperature. We have pH, right? So acidity, right? As we've spoken about, more hydrogen protons get produced when we exercise. We have now a actual molecule, 3-carbon molecule that gets produced in the middle of glycolysis. That acts as a feedback signal, which shifts this association curve to the right, which changes the affinity of oxygen. Okay, so really, really important, even though it's redundant stuff. Okay, and that's good. We want oxygen in our working cells. Okay, so that was oxygen. The last point that we talk about is carbon dioxide, right? We've spoken about how oxygen gets transported in and towards us, working tissues, the affinity of red blood cells. How does carbon dioxide get out? Okay, so we have a slightly greater amount dissolved in plasma relative to oxygen. We have 20% of it that's bound to hemoglobin. Okay, and if you recall, again, when we're talking about saturation of oxygen, it's almost 100% at points in time in our body. Okay, so generally 20% is bound to hemoglobin, 20% is in plasma, and when it's bound to hemoglobin, it's not the same as oxygen. It's not bound to the heme; it's bound to the globin portion in hemoglobin. Okay, so that's a good distinction to keep in your mind. And you get this thing called carbaminohemoglobin. Okay. And as we'd expect, where there's low pressure, partial pressure carbon dioxide in the lungs, we would expect the carbon dioxide to flow down that partial pressure gradient and be released from hemoglobin there to be exhaled. Okay. We have spoke about bicarbonate before, so this came up in a previous lecture or two, but just to cover it again here, Bicarbonate is a buffer system that we have in blood, and it's really, really important for getting carbon dioxide from a working cell into the plasma, but as you can see, very important to store it in blood to be transported to the lungs to be exhaled, okay? So this is the molecule for bicarbonate, and this is the buffer system. So depending on which side of this buffer system is more, has a greater quantity, it'll push and shift the buffer one direction or the other. And the whole point of a buffer system is to maintain equilibrium in pH as best it can. And typically, depending on the buffer system, they do a quite a good job, okay? Okay, that was my side note about buffer systems. They're actually kind of cool and really interesting, especially if you love biochemistry and things of that nature. You come across them all throughout chemistry, but biochem in particular. And yeah, I'd support your further investigation into buffer systems. I digress. So when we're talking about bicarbonate and the buffer system in blood, we have this process where carbon dioxide is present. It will meet bicarbonate, which then essentially gets transported as this ion. But now the issue with this is it's great because it can transport out into the plasma of blood and then get circulated to the lungs to be exhaled. However, because this has a fairly negative ionic charge and it leaves the red blood cell, that leaves the electro gradient, so the electric charge you can think of in the red blood cell, askew. So what ends up happening is chloride comes in to fill for this negative charge in the red blood cell to maintain that balance. All right, so it's called a chloride shift. So chloride is Cl negative, so you have 3 of those coming in to make up for that change in electrogradient. Okay, the hydrogen proton itself binds to globin, so hemoglobin itself is a buffer, and from that we get this reduced affinity and we see a shift to the right. Again, we've now listed off 4 things, right, that cause a right shift in the oxyhemoglobin dissociation curve, right? So if you're given this on an exam or a quiz, you should know that and be able to draw and explain that when we're exercising, and you should figure out and remember which 4 influences shift things to the right. Again, it's anything that we want to decrease the affinity of oxygen to hemoglobin and increase unloading of oxygen to working tissues, okay? And so again, that shift to the right at any given partial pressure of oxygen will decrease the percent of saturation, okay? And we want a decreased saturation percentage of oxyhemoglobin if we're exercising. Okay. I said that probably about 9 different times in 9 different ways, but I really wanted to try to make that as clear and apparent as possible. All right, I'll leave you with that. This is definitely a lecture you should go back, dive into, draw out yourself, try to figure out the how the partial pressure changes with a shift, curve shift, and yeah, and you should be good to go. Okay, thanks. Cheers.